This screencast is going to talk about two problems that can be thought of as search problems. I talked about in the last screencast that many problems in computer science can be thought of as search problems. And the problems we're going to talk about here are two of the most important ones, the traveling salesperson problem and the 0-1 knapsack problem. And what we're going to do is we're going to talk about how you would apply exhaustive search to those problems. So remember how that's going to work. The idea is that we generate a list of all the potential solutions to the problem, and then we evaluate all those solutions, disqualifying infeasible ones, and keeping track, if an optimization problem, keeping track of the best one found so far. So the first one of these problems is the traveling salesperson problem. Given n cities with known distances between each pair, find the shortest tour that passes through all the cities exactly once before returning to the starting city. Now, this is just one way to set up the problem, think about the problem. There are lots of applications to the traveling salesperson problem. One being in robotics, moving a robot arm in the most efficient fashion to potentially, say, solder a circuit board. Another one would be for delivery services. So you can think of the traveling salesperson problem as a graph, a weighted graph, connected, and you can then think of the search space as a tree where the branches of the tree, focus here on A for a second. The A has branches to each of the other cities that it's possible for it to be visit, and then B, since it's already, if I go down this branch, A and B have been visited, so B could go either to C, D, or E, etc. We'll talk about search space trees a lot later in the course. For right now, though, I just wanted to give you some idea of what they might look like. Finally, you can use the search space tree as a way to think about how many different potential tours there are to solve the traveling salesperson problem. So you might take a second and think about what it means in terms of the number of tours there would be for a traveling salesperson problem like this one with 5 cities. So this slide shows a very simple example of the traveling salesperson problem with only 4 cities. I don't want to spend a lot of time on this slide, but I want to point out that in terms of the picture here, this is a complete graph. And we'll usually assume for the time being that all the traveling salesperson problems are complete. That's not really restrictive because we can always add edges that are very long or have heavy weights. So one way to think about solving something like the traveling salesperson problem, let's just be greedy about the whole thing. Let's just start someplace and take the nearest neighbor. So in other words, what that might mean is suppose we start at A. The nearest neighbor to A is B. Okay, C is 3 away and D is 6 away. So we'd go to B. Then the nearest neighbor to B is C. So we'd go to C, and the nearest neighbor to C is D. Okay, now we've visited all the cities, but remember part of the traveling salesperson problem is that you've got to do a circuit, a tour. So we go back to A. So the length of that tour is going to be 11. So this is a pretty simple example that shows that greedy does not always find the optimal solution. Just consider the tour that goes A to B to D to C and back to A again. That only has length 10 versus the tour that we found originally has length 11. Notice, and you should kind of verify this, I think, by trying it out, I can make this 6 as large as I want. And the tour found by nearest neighbor, no matter where I start, would still be A, B, C, D, and A. So we could make that tour found by greedy have a very long length, make this say 100, and so you'd be much better off. You can see that greedy is not guaranteed to even be close to the optimal solution in certain examples. So here's a sample of tours. Notice they all begin at A and end at A. One thing to realize, of course, is that once you have one of these tours, it really doesn't matter what city you start at. the length will be the same. That's important for the number of tours that we'd have to check. We really don't have to worry about what we can fix one vertex or one city to be the starting city, and and we don't have to change that in terms of looking at all the possible tours, because starting in another city, if we did the cities in the same order, then it wouldn't change the length of the tour. All right, so if you should look at these through this example and notice each potential length here occurs twice. Now, that's actually telling us something. I mean, that's somewhat of a things may occur more than twice, but in this example, they just appear twice, and there's a reason. And you should think about, well, what is that reason? Why is this tour giving you the same length as that tour? So take a look at that, and then think of, because of this, suppose you had 5 cities. Well, we know already that the starting city doesn't matter. So that would mean that we really have the permutation of the other 4 cities are the things that would matter. So how many distinct tours would that give you? But then also think about this duplication here. Why are these tours guaranteed to be the same length? And why is the first tour guaranteed to be the same length as this last tour? And why is this tour, 13, with length 13, guaranteed to be the same as this tour? And then try to come up with a formula for n cities. So pause the screencast right now, give that some thought. So hopefully you paused the screencast and thought about it. Basically, what the result is that for 5 cities, for instance, the number of tours that you actually have to examine is going to be 4 factorial. Okay, so we can ignore the starting city, and then divided by 2, because you can reverse the order. So really, to find the shortest tour, you're really going to have to do n minus 1 factorial over 2 tours to check. The next problem I want to talk about is the 0-1 knapsack problem. So what does the 0-1 mean? I'll explain that in a second. So the 0-1 knapsack problem can be thought of as you've got n items with weights. Each item has a weight and a value, and you have a knapsack of capacity W. So you can think of this as a thief walking into some sort of antique store maybe, and all the items in the antique store are labeled conveniently with their weights and values, and the thief wants to steal as the most valuable subset of the items that will fit into the knapsack. So one example would be the knapsack has capacity 16, and we have these different items. Item 1 has weight 2, value 20. Item 2 has weight 5, value 30, etc. Potentially, depending on the setup here and the weights and values of the items, every subset has to be checked. It may only need to be checked to see if it would fit, but if it would fit, then you have to compute the value and then keep track of those values as you go along. So here's an example of all the subsets. I left out the empty subset. Presumably at least one item would fit into the knapsack. And so here are all the possibilities. The largest one is 80, which involves putting in 2 and 3 into the knapsack. So you might work through some of these, make sure you understand what's going on. Notice that some of the larger subsets are not feasible. That means that the weights add up to be more than 16. Okay, and so they won't fit into the knapsack. So once you know that, you don't even need to compute what the value is going to be. So notice that for a traveling salesperson problem, we basically have to consider permutations. We're going to have to generate all the permutations of some set of things. And for the knapsack problem, we're going to have to find all the subsets for such things, for a set of things. The last problem I want to talk about is the assignment problem, and I'll just give you a quick overview of this problem. You've got some number of people and some jobs, and what you'd like to do is assign the jobs to the people so that all the jobs get done, all the people have a job, so there'll be a one-to-one and onto mapping, and you want to do that in such a way that minimizes the total costs, where the numbers in this matrix represent the costs. So person A can do job 0 with cost $5, job 1 costs $2, etc. So you can think of this as the different people have different expertise. They can do some jobs more efficiently than others. So that explains the different costs. The question to start with here is, how many assignments are there actually? So take a few seconds and think about that and pause the video. So if you think about it, basically what you need is a permutation. You want to find all the permutations of the jobs and assign the first thing in the permutation to person A, the next thing to person B, person C, person D. So that means there's n factorial different assignments. So again, given this example, if you do the assignments, if you just start sort of listing the assignments here, 1, 2, 3, 4 gives you a total cost of 17, and you can check that. That's basically the diagonal here. 1, 2, 4, 3 is going to be 5 plus 9 plus 8 plus 9, so that's going to be 26, etc. If you did a simple greedy algorithm that just first assigned some job to the the 0th person, person A, give them 2, then you can't assign that a job again. So then when you get to the person B, you give them this job with 3. Then you can't assign that job to anybody else. So here, person C would get this job, which is job 0, which is 5, and then person D would get this job, which costs 7. If you add those up, you get that that's 17. But it turns out that the optimal solution is 14. So at least this greedy algorithm is not correct for the assignment problem. Again, but notice here what we got. We basically need all the permutations again if we're going to do this problem by exhaustive search. So how do we generate these permutations and subsets? These are what are called combinatorial objects. These are just the most simple examples of those things that occur in a computer science. And the easiest way to think about generating them is recursively. This leads to pretty straightforward implementations. So you should think about this. We'll go over it a lot more in lab, but you should think about how you might do this. One way for doing subsets or permutations is to, again, think about it recursively and assume that you've got a black box that'll solve the problem for n minus 1 things. So all the subsets say of n minus 1, and then use those subsets to generate all the subsets for n things. Notice that the subsets for n things will contain, half of them will contain the nth item, and the other half won't contain the nth item. So think about how you might be able to use the subsets of a set of size n minus 1 to be able to generate the subsets of size n. So this is just a quick introduction to some problems that are important in computer science that can be thought of as search problems and can be solved using exhaustive search.